Hey guys, welcome back to Artificially Intelligent AI. My name is Janetta, and today we're looking at another LeetCode problem. We're also looking at another binary tree problem. We've done a few of these before, links in the description if you want to go check those other videos out. But today, the focus of our video is going to be validating a binary search tree. So before we get too into the description of what we're doing, let's actually talk about just the intuition behind what is a tree, what is a binary search tree, just to refresh our memories. So a tree is going to be a data structure that, and specifically a binary tree, because that's really all we're looking at here. A binary tree is going to be a data structure that has a node, and a node can have leaves. So we can have a left and a right child to a node. So the way that we would define this is we would say that in this case, the node has a value of 1, and we would say node.left in this case is equal to a node with the value 2, and node.right is equal to a node of value 3. So that's how this works for this specific example. If we're talking about a binary search tree, so that word search, it's going to help us know how to traverse the tree, what to expect when we're traversing the tree. So a binary search tree is going to have a added layer of implication that if I have a node, that any node, the node to the left is going to be less. So the left is going to be less than the value of the node. And the right is going to be greater. So another way to say that is we're going to say that node.val, because remember, val is how we're going to call the value at the node. So node.val is going to be less than node.right.val, and node.val is going to be greater than node.left.val. So that's another way to think of that. And in addition, every subtree in a binary search tree also has to be a binary search tree. So let's look at this example. If I say I have 3, 2, 5, 1, and I can throw 1 here too just for fun. Okay. So as I start to traverse downward from this tree, I start with my node of 3. Its value is less than 6 and greater than 2. So the first layer, that looks like a valid binary search tree. If I then just look at this subtree here, 2 is less than 5, and then 2 is greater than 1. So that also looks like a binary search tree. However, if we notice here, we have this value 5. It is to the left of 3, and 5 is greater than 3. So this is actually not a binary search tree, since it breaks the rule that every value to the left of a node has to be less than the value of that node, and 5 is greater than 3, but 5 is to the left of 3. So that breaks the rule. So this would not be a valid binary search tree. So let's get into the intuition about how this problem is going to be solved. So with most of these types of binary search tree problems, a really common approach to solving them is it's definitely going to be recursion, and it's going to be some kind of depth first, usually recursion, where we traverse the tree all the way down to the bottom, check some things, work our way back up, and then down the right-hand side, and work our way up to the top of the tree. This is kind of going to work like that, but with a little bit of a twist that we're going to be doing the work up front. So we're going to start doing the work, doing the checking at the top, but then we are going to work our way all the way down and then work our way back up, like you would expect in a normal tree traversal. So let's talk about the logic like we talked about above. What does it actually mean for a binary search tree to be a valid binary search tree? Well, it means that when I am at a node and I look at the value of the node, I'm expecting that it's going to be less than the right and greater than the left. But we have to have some way to hold on to the value, because remember this problem up here that we had, the problem was with 3 and 5. And you wouldn't know just from looking at this subtree alone that we had an invalid binary search tree. We have to have some way of holding on to this value from above. So the way we're going to do that is by passing a parameter along with us. So the way that we're going to do that is instead of just calling node.val, I'm going to actually be storing a low value, like a lower limit, and a high value, which is going to be an upper limit. So to start, I'm going to just set low equal to negative infinity and high equal to positive infinity, so that I know any value that gets passed in is going to work. So that's going to be for my first value. So I start at 5, and I ask myself, first I always check to see, is there actually a node here? Because if there isn't a node, then when I try to call its value, I'm going to get an error thrown back at me. It's going to say that none type doesn't have an attribute value. So to avoid that, I first check. So if we look at the solution, this first line in our helper function, if node is none, we're going to return true. And that's really going to, what that's going to do is when we get to a leaf node, it doesn't, when I check to see if it has a left or a right value, it doesn't. So that is what's called a leaf node. And that is a binary search tree, a sub-binary search tree in and of itself. So this would be a valid subtree. So I check to see if it exists. It does. So then what I'm going to do is check. So right now my lower limit is negative infinity. My higher limit is positive infinity. So I ask, is 5 greater than the low and less than the high? Yes, it is. So I'm not going to return false. I'm just going to keep on going. So then this is where the recursion is going to happen. Now I jump into this return statement, and this is where it gets a little bit different. A little different than what you would normally see in these kind of problems. And I like the way that this is set up. You're actually returning a Boolean, but it's going to be an and statement. So essentially what needs to happen is we need the left subtree to be valid and the right subtree to be valid. So we're checking, is the left true and is the right true? So we have some choices. We'll either get true and true, meaning that the left subtree and the right subtree are valid, and then it's going to return true and true, which is true. And then you can see, because of this and statement, if either of these are false, if you get true and false, or if you get false and false, or false and true, either way, that is telling you that at least one of the subtrees is not valid, and that invalidates the entire thing, right? So I like how that works, that we're returning this Boolean. It's really clever. Okay, so let's traverse this tree and just see how this logic works. So I'm right here at 5. I already checked the condition. It's less than and greater than positive and negative infinity, or vice versa. Now let's jump into the helper function. So what am I passing? I'm passing two things. So let's look at the left, because the left comes first. I am passing in node.left, which is going to be 3. I'm passing in the low is still going to be negative infinity, but now the high is going to be the current node's value, which is 5. So now I get to 3. Now I ask myself, is the node none? No, so we can keep going. And then we ask ourselves the validating question of node.val. So is 3, is it less than negative infinity? No, it's not. Is it greater than 5? No, it's not. So it passed both of those tests. And then we go back again to the recursion, to the return statement. So again, we're traversing. So this is going to be a depth first search. We're going all the way left before we come back up and around. So now, what are we passing? So we're still going left. So we're going to end up here at 1. Low is still equal to negative infinity. High is now going to be equal to 3. So high is now equal to 3. Now I'm asking the question of 1. So 1 is not none. 1 is greater than negative infinity. 1 is less than 3. So it passes. And we keep on going. So now we still go left. But look, when I pass for the node 1, when I pass node dot left, there's nothing there. So in this case, it's going to be none. So what do I return when I have none? I return true. So what's getting returned to 1 from the left-hand side is true. And now I'm right here. Now I'm in this return statement from the node 1. And I just got, so in this return statement, it's saying to return the helper when I go to the left. And that I just got back the value true. Oops. I just got back the value true. Now I need to do the helper to the right. So now I'm going to go to the right of 1. Again, I'm going to have none. So I'm going to return true. So now this node 1 has the return statement of true and true. So 1 is going to now return true to 3. So now I'm at 3. So now I'm at my return statement from 3. So remember, 3, it went left. It did helper for the left-hand side, and I just got back true. So now I need to look at the helper for the right-hand side. So now I'm going to do the same thing. I'm at 4. So we already know how this works. Oops. I go left first. It's returning true because there's nothing there. I go right. It's returning true because there's nothing there. So that means that 4 is returning true and true. So 4, when it returns to 3, it's going to return true. So 3, if we look at 3's subtree, 3 is returning true and true. So 3 is going to return the value of true to its parent node. So we just traversed the whole left side, and what we found, so this 5, this was our entry point. This is where we first entered this return statement. And what I just did is I traversed the whole left side. I went all the way left, came back up, went right, came all the way back up. So now the whole left subtree is returning itself as true. So when I'm in this return statement, this is my very first return statement from the beginning. for the node 5. Return, so I did helper to the left. My lower limit, we didn't talk about that. I kind of glazed over that. When I was here at 4 and I looked at my helper, what happens when I go right? Well, let's look here. When I go right, I pass node.right. I pass the lower limit is now the value. So now I get helper low equals 3, and high, what was high? High is 5. So low 3, high 5, does 4 fall in between 3 and 5? Yes, it does. Okay, so notice that when I go left, I'm setting an upper bound, but when I go right, I'm setting a lower bound. That's what's happening in this call to the helper when I go on the right-hand side. So when I'm here at 5, I have, I have lower, well, we already did the left-hand side. So right now, the low, as I pass into, so let's see, helper. Let's go right. Let's set the lower equal to 5. The upper at this point is equal to still that positive infinity. And 6 is greater than 5, less than infinity. So this is going to return a true from the right-hand side. So I'm getting at the very end, I'm getting true and true. So my entire return is going to be true. And if you look, the only thing in the actual function outside of the helper function, the only piece of code in the function isValidBST is just the return statement, whatever the function helper is returning. And in this case, helper is returning true. So the whole entire function, the original isValidBST function, is going to return true. So what were the key points to this problem? It was setting these low and high limits as parameters to the function. Otherwise, the parameters would not be passed along the way that we want them to. So by setting them as parameters, they update as we use recursion, as we go down and up the subtree. That is it for this one. I'm going to start doing some more difficult binary search tree, graph, linked list problems in the coming weeks. I wanted to make sure that we're covering our bases with these easy, kind of more fundamental problems so we really understand them before we start branching out. This is definitely one of the fundamental problems in my opinion. So hopefully it was helpful. If you found this video helpful, definitely like and subscribe for more content. And please connect with me on my other social media links. I have them listed in the description. See you guys next time. Thanks.